Okay, so today we're looking at binomial expansions. And if you remember in a previous video, we looked at finding the expansion of a form like this, a plus b to the power of n, but we did it using Pascal's triangle. And Pascal's triangle gives you the coefficients in front of the numbers. But today we're looking at an explicit formula, and this is sometimes called the binomial theorem. And what's nice about this is if n is really large, we don't want to compute all the rows of Pascal's triangle, but we can just plug in the numbers here and it becomes quite easy. So a few things to note. Firstly, remember this definition of n choose k. I'll just write it over here. So n choose k is defined as n factorial divided by k factorial times n minus k factorial. So these give us all the coefficients essentially. So this would agree with the rows of Pascal's triangle, but it's just a more explicit formula and it's easier to calculate with a computer, for example. And then what do we have? So we have the summation over all the coefficients, and then we have these terms a and b. So a is raised to the power of n minus k, b is raised to the power of k, where k goes from 0 to n. So the powers of a are decreasing linearly and the powers of b are going up linearly. So that's the pattern there. So there's also a couple other things to be careful about. So in this definition, we need to sum from k equals 0. And then that begs the question, what is n choose 0? And then, if we plug it into the formula, then we get 0 factorial over, not 0 factorial, so we get n factorial on the top, n factorial, but 0 factorial on the bottom, n factorial on the bottom as well. And now it's good to be aware that 0 factorial, we just define this to be 1. So then we have n factorial over n factorial, and this comes out to be 1. It's just convention, so it agrees with the actual combinations if we expand this out. And so also, this also equals n choose n. So this is going to be the same formula, so we also set this equal to 1. And then we're ready to go with this formula. Okay, so now let's look at an example just so we can get practice using this. Let's look at expanding 3 minus 2x to the power of 5. So in this example, I'm going to set I'll just write it up here, a equals 3, and then b equals minus 2x. So if we plug these numbers in and use the formula, we're going to get, so n here is 5, so we have 5 choose 0, and remember we're just defining this as 1. But then we write a is b, so 3 to the power of 5 times b, which is minus 2x, to the power of 0. And then we carry on, so 5 choose 1 then, because we're summing from k, going from 0 to n. 5 choose 1, k is now 1, 3 to the power of 4 times minus 2x to the power of 1. So this is now going to contribute, and then we carry on, 5 choose 2 times 3 cubed times minus 2x squared, and then 5 choose 3, 3 squared. I'll be a bit quicker now because it's the same pattern essentially. This is power of 3, then 5 choose 4, this goes down by 1, this goes up by 1, and finally we have 5 choose 5, which again, remember we said this is 1, and then 3 to the power of 0, that's going to go away, and minus 2x to the power of 5. So this is just using the formula. And I'm quickly going to do another line where I just give you the values of these combinations. So we said 5 choose 0 is just equal to 1. So we have 1 times 3 to the power of 5. And actually this is to the power of 0, so this vanishes. I can just take away the 1 as well, because anything to the power of 0 is equal to 1. And then 5 choose 1, if you put this into a calculator, this comes out as 5. And then we have times 3 to the power of 4 times minus 2x. 5 choose 2 is actually 10. Then 3 cubed times minus 2x squared. 5 choose 3 is actually the same as 5 choose 2. This just equals 10. So we have 10 times 3 squared times minus 2x cubed. And then 5 choose 4, because of the symmetry, this is the same as 5 choose 1. So this is just 5 times 3 times minus 2x to the power of 4. And finally, we said 5 choose 5 by definition. This is just 1. 3 to the power of 0 is also 1, so we just get left with minus 2x to the power of 5. And then it's just a matter of algebra. We can simplify this. I'm not going to do all the calculations here, but if you go away and work out these steps, or just use a calculator, this is going to come out as 243 minus 810x plus 1080x squared minus 720x cubed. So we've expressed this bracket, this binomial expansion, as a simple polynomial, and this is one of the order 5. And whenever you're dealing with these expansions, the highest order is always going to be the power that you're raising the bracket to. So now that we've seen how to use the formula, we're going to do one more example and we're going to see why this is actually a really useful trick. Okay, so now I want to show you this example because it turns out it's actually quite useful. So this is a binomial expansion of the form 1 plus x, and we raise this to the power of n. And if we just start plugging stuff in, we're going to see some simplifications because we have n choose 0, this is just 1, but then we have 1 to the power of n. But we know that anything to 1 to the power of anything is just 1, so this is actually going to cancel as well. And then we get x to the power of 0 plus then n choose 1 of 1 to the power of n minus 1. It doesn't actually matter what n is here. Then we have x to the power of 1 plus n choose 2, 1 to the power of n minus 2. Again, this is 1, x squared, and this carries on. So we can actually simplify this by just getting rid of all the 1's. And this is also 1, so then we have 1 as the first term, plus n choose 1 times x, plus n choose 2 times x squared, and this carries on, so we have n choose 3 times x cubed as the next term, and this carries on all the way up to the nth term, which is just going to be n choose n, which is 1, and then times x to the power of n. Now the reason this is really useful, this expression, is because we can use it to approximate some numbers. So let's say we want to find the value of 1.01 to the power of 5. Now we can actually use this formula with x equal to 0.01. And since x is really small, this is actually going to be a good approximation by just truncating it after a few terms. So we don't have to input it for all these x's. We could just calculate the first few terms, and this would give us an approximation. So let's just do that. And if we approximate for up to, we're going to approximate up to x squared term. So we're going to have 1 plus n here is 5. 5 choose 1 times x, which is 0.01, plus 5 choose 2 times 0.01 squared. And this is something we can evaluate very easily. This is 1 plus 5 choose 1 is just 5, so this is plus 0.05. Now 5 choose 2 is just 10, so we have 10 times 0.01 squared, and this comes out as 0.01, so we have 2 zeros now. And this is something we can just add up, so this comes out as 1.051. So this is our approximation, and if we compare it with the actual value, if we put this into a calculator and work out the exact value, this would come out to be, we just add a few more digits, we have 0.501. So the stuff in black, this is the exact expression for 1.01 to the power of 5. And we see by just doing this approximation, by just inputting it into the first few terms, we actually get the exact answer up to 3 decimal places, which is really nice. So it becomes a much more efficient way to approximate a number like this. And computers and calculators, they use all these type of techniques to speed up calculations. Because if you only want the precision to a certain degree, then you don't need to work out the number till infinity, you can just truncate it after some point. So this is just something I wanted to show because I thought it was quite a neat trick using the binomial expansion.